Hi, we're recording live. These notes are about trig identities. Here's like the reason we study trig identities. These are the kinds of problems that you're going to get. So each of these is an identity, and you're supposed to verify that it's an identity by using algebra to show that both sides are the same. All right, so why is this important? Nobody actually cares about any of these particular identities. It's not like this is going to come back in calculus. There's two reasons to know it. The first reason is there's a couple of key identities that's going to be the key to unlocking all of these, and those do come up in calculus a lot. Like in calculus, you do a thing called integrating, and certain problems are almost impossible to integrate unless you recognize where you can make a substitution using a trig identity. So, like, yes, it does appear. Then the other half of why we do this is it's giving you practice with algebraic fluency, like working with fractions, factoring, like all of those things. I guess kind of the third reason is it's algebraic problem solving. So each of these problems, there's usually like 3 or 4 different directions you could decide to go. And sometimes you might head in one direction and it's getting messier and grosser, and you'll decide to back up and head in a different direction. So each problem is like a tiny puzzle. They're not super hard puzzles, but they are like little puzzles. And so that's like very authentic to how you need to do algebra when you're doing algebraic problem solving in general. So those are the 3 reasons. Little bit in calculus, good algebraic fluency, good algebraic problem solving. All right, notes. You already know these things. Remind your neighbors. Fill in the top section of that right now. All right, here we go. We're back. Hopefully you remembered these. If this was a little rough because you haven't thought about these, in several months, that's okay. Be aware, you're going to need to know those kind of right off the top of your head for this unit. So tangent, is sine over cosine. Cotangent, a lot of people consistently write 1 over tangent, which is not wrong, but it's going to be really useful to remember this as cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. Okay, so I'm going to start with the most important of all the identities. It's called the Pythagorean identity. Like 40% of all math is just the Pythagorean theorem. Go ahead and fill in a circle. This is supposed to be a unit circle, so that's 1 and that's 1. This is 0, 0 here. Go ahead and fill in a point and an angle. These are coordinates x, y. And then just verbally remind your neighbor, like that height. Oh, let's draw better. Okay. That height, yes, it's the y coordinate, but remind them what trig function describes that, what trig function describes that. Go. All right, agreed. So the y coordinate is the same thing as the sine of the angle. The x coordinate is the same thing as the cosine of the angle. All right, so, and remember that's also, here, let's write x equals and y equals here. So if this triangle right here, this right triangle, if we were going to write the Pythagorean theorem, we'd say, okay, so that leg is x squared, that leg is y squared, that equals, what does it equal? How long is that thing? Are you nervous? So definitely distance 1. So the Pythagorean theorem just says x squared plus y squared equals 1 squared, which I'll just write as 1 because it's silly to write 1 squared. All right, so here's the identity. If x is cosine and y is sine, you can make the substitutions, and you've got, write it down this way. This might be a new way of writing it down for you, but write cosine, and then that 2 is an exponent, and then sine, and then the 2 is in the exponent, equals 1. So this right here, if you want to make some decorative marks, you could. That's the Pythagorean identity. Okay, here's a quick note. If you haven't seen this notation before, if I write cosine squared theta, that's the same thing as cosine theta quantity squared. So even though the 2 is kind of written inside the function, it is really talking about this. Like you evaluate cosine, and then you take the output of cosine and you square it. Everybody writes it this way. We haven't been up till this point, but you should know it so that when you see it, you won't get confused. All right. let's see, what else? Them. Okay, so that's the identity. You're going to use this all the time. I'm going to say you probably use this on like 60% of all the problems. So here's how you'll actually see it. Imagine you were going to solve for, or like isolate either the cosine or the sine. So if I isolate cosine, I'd subtract sine squared. So I'd have like cosine equals 1 minus sine squared. Cosine squared is 1 minus sine squared. Tell your neighbor out loud, what does it look like if I isolate sine squared? If I subtract cosine squared from both sides, then I'll have sine squared is 1 minus cosine squared. Okay, so the way that you're going to use this very, very often is you'll see this as part of your problem. You'll see a 1 minus sine squared, and you'll think, oh, that's just cosine squared. So you'll make a substitution, and that will happen dozens and dozens of times. All right, question so far. So there's actually 3 different versions of the Pythagorean identity. The one with sines and cosines we just did. Let's write it again. Cosine squared plus sine squared is 1. Okay, I'm going to pause the video and ask you, if I was going to do something to both sides of the equation that will make there appear a tangent all of a sudden, like I want to turn some of these terms into a tangent, what could I do? All right, yes, so if we divide both sides here by cosine, let's do that. So cosine squared plus sine squared equals 1. So I'll divide everything by cosine squared. So that over cosine squared, that over cosine squared, that over cosine squared. All right, so cosine squared divided by cosine squared, anything divided by itself is 1. Then here we've got sine squared over cosine squared, so that's tangent squared. And then remind your neighbor real quick, 1 over cosine squared, what's that thing? Oh, all right, so 1 over cosine is secant, so 1 over cosine squared should be secant squared. Somebody asks, why is it tangent? That's a great question. Let's sort of like pull out a box here to see why it's tangent. So I've got sine squared over cosine squared. I'm going to rewrite it this way. So the way that I've notated this, it really is you're squaring the numerator and squaring the denominator separately, but that's the same thing as if you'd done sine theta over cosine theta quantity squared. Like if you think about if I have like triangle over square quantity squared, that squared applies to both numerator and denominator. So that's why this ends up being tangent squared, because sine over cosine is tangent, and I'm squaring it. So that's how this turns into that, which is a fine question. Okay, do it all one more time. So this is a version of the Pythagorean identity that's got tangent in it. Figure out how could you get one with cotangent. Go. Okay, we're back. So here we divided everything by cosine because I knew sine over cosine is going to give me tangent. I want cotangent. Up at the very top of your page, you saw that cotangent is cosine over sine. So if I divide everything by sine, well, rather sine squared, that'll give me cosine squared over sine squared. So let's divide everything by sine squared to end up with what we want. And then we'll simplify. So cosine squared over sine squared is cotangent squared. Sine squared over itself is 1. And then 1 over sine squared is cosecant squared. So those are the 3 different versions of the Pythagorean identity. They all appear sometimes. My recommendation is don't memorize them all, but definitely memorize that first one because you see it all the time. If it turns out you might need one of the other ones, I just showed you how you derive it. You just think, oh, what if I divided both sides by sine squared? What if I divided both sides by cosine squared? And so you can always rederive the other one if you need to. I mean, if you're good at memorizing stuff and it's easy enough, then fine, do it, because they do appear. But if, it feels fiddly to memorize, the first one's the important one. So this is the kind of situation that you're going to use these for, which I sort of showed you to start with. Like we've got this equation that I'm claiming is an identity. We're going to manipulate both sides until we see that they're the same. I'll pause it and let you talk about it for 30 seconds. You'll see what you're going to see, and then we'll solve it together. Okay, we're back. So I'm about to show you one version of this. There's usually, 4 or 5 different versions that work. The thing that I noticed right away is the 1 minus sine squared. If you remember from the front side, 1 minus sine squared is the same as cosine squared. So I'm going to make that substitution. So I'll have sine x cosine x divided by cosine squared x equals 1 over cotangent. So now one of these cosines gets divided by one of the 2 cosines in the denominator, because cosine squared is the same as cosine times cosine. So one of those 2 cosines in the denominator divided out. And so now I've got sine over cosine, which is just tangent. You might think like, okay, now we're done, because you look at this and you think, yes, that's obviously true. Take it one more step to make it really, really, really obvious. So cotangent, you could rewrite as 1 over tangent. And then 1 divided by 1 over tangent, you multiply by the reciprocal, and we've got tangent and tangent on both sides. And so now it like really is obviously the same. So that's so this is kind of a simpler one. But that's the kind of thing you're going to do is you'll make some substitutions, you'll do a little algebra until both sides are the same, and that verifies that it's always true no matter what. All right, here are some useful algebra moves. So one you saw already was recognizing the 1 minus sine squared as being cosine squared, or the other one, 1 minus cosine squared is also sine squared. So that's going to be a really helpful move. Another helpful move is rewriting everything in terms of sine and cosine. So if you've got like cotangent times secant, for example, and you need to figure out like how do you manipulate those, cotangent you could rewrite as cosine over sine, secant you could rewrite as 1 over cosine, and now you see that things are like starting to divide already. So that's oftentimes a helpful thing you could do. Conjugate. So the idea of a conjugate we've met before. We will meet it again. In this context, like let's pretend you had like 1 plus sine x. That's not that helpful. It would be really great if we had 1 minus sine squared, because that we know how to do something with. But this by itself, we don't know how to do anything with. So here's what it would look like. Let's put it over triangle. So it appears in some fraction with some other stuff happening. So something you can do is multiply by the conjugate. Remember before we had this idea that the conjugate, if you've got like 1 plus something, the conjugate would be 1 minus the same thing. And the same idea applies here. So we could multiply it by 1 minus sine over 1 minus sine. Take a little minute and work out with your neighbors kind of what happens when you multiply out the numerator. Okay, here we go. So multiplying it out, 1 times 1 is 1. 1 times negative sine is negative sine. Sine times 1 is positive sine. So the negative sign and the positive sign undo each other to make 0. And then here we've got negative sine squared. So that's why it's useful to multiply by the conjugate. It's because it lets you get a 1 minus sine squared if you need it. And then in the denominator, we still have this thing. And then in the numerator, now we can replace it as cosine squared. And like maybe that's the move you needed to do. Lastly, combine fractions or split apart fractions. Combine, you would like make denominators the same. Split apart would be if you've got like triangle plus square divided by circle. Oh, let's not. That makes it look like I'm dividing by 0, huh? Smiley face. That's the same thing as rewriting it as 2 fractions. So triangle over smiley face plus square over smiley face. So you can definitely do that. Sometimes that will simplify things. I think I've said enough, maybe too much. We'll whiteboard these couple of problems. So each of these involves one of the tricks. You can flip the page over for the hint for which of the tricks it is. But give it a try without it first. Good luck, team.